Welcome, ladies and gentlemen. Let's take a look at the convergence versus divergence of series. So we have to be able to select and apply an appropriate tool to show whether or not a given series converges or diverges. But I don't want you to think that you need to let go of all your informal, thought processes that we've already developed, like rates of growth and rates of change. What grows more quickly? Linear, power, exponential, and factorial, We can still use that stuff to intuitively determine whether we think it'll converge or not, and then prove it algebraically using one of our tests that we've been working with. Take a look at the first one. While this is not a geometric series, doesn't it look a lot like a geometric series? In fact, a geometric series that we know whether it converges or not. So, what test did you use to show the convergence or divergence of this one? Marissa?
I guess the direct comparison test.
Great. And what did you compare it with?
2/5 all to the n.
Absolutely. And so who else used direct comparison? Direct comparison? Great. We see that this, looks a lot like 2 to the n over 5 to the n. All right. In fact, that plus 4 on bottom as n gets big is going to be inconsequential. And yet, it's what allows us to use the direct comparison test, because that plus 4 on the bottom makes the denominator slightly larger, slightly larger, ensuring that the fraction will be a smaller value than 2/5 to the n, meaning we can use it for direct comparison. So if we can compare this, to a known series, that is a series we know to converge, and this is forever less than that series, then it must also converge by direct comparison. In order to do that, though, we should say, let's let this equal series A, the sum of A sub n, and then let's compare it with, we'll call series B, and let's let series B be the sum from n equals 0 to infinity of 2 to the n over 5 to the n. This is a geometric series with r equals 2/5, We could rewrite that as 2/5 all to the n, which is less than 1, so that converges. Okay, so we've chosen a series to compare it with. We know that this series converges. So my original series is forever less than or equal to my known series, which converges, for some n greater than or equal to n. In fact, this is going to be less than or equal to it for all of them. Okay? Therefore, my original A sub n must converge by the direct comparison test. So did we have to do the ratio test? No. Could we have done the ratio test? Yes, we could have done the ratio test. Now that may or may not have resulted in some algebraic, difficulties or not, but we certainly could have done the ratio test. However, if we recognize a known series that we can compare it to, then that's the quicker, more efficient route. Awesome. All right, so let's take a look at number 2. Number 2, is that geometric? No, and in fact, it has that factorial expression too. And so this is a great place to apply the ratio test. This is where, we can really see the power of the ratio test and its utility. So the ratio test is a powerful tool, and it encompasses a lot of different categories of series types. So let's go ahead and see if this converges by applying the ratio test. In the ratio test, we consider the limit as n goes to infinity of the absolute value of a sub n plus 1 to a sub n. And we see if we can simplify, We want to see this ratio be less than 1. If it's less than 1, we know that my series will converge. If it's greater than, 1, then the series diverges. And if it equals 1, then the ratio test is inconclusive. It doesn't tell us one way or another. So let's go ahead and see if we can't plug in here. Again, I'll be doing multiply by the reciprocal just to save space from forever after. So here we go. 2 to the n plus 1 over n plus 2 factorial. Did everybody see how we got that? N plus 2 factorial out of 1, good. And then my a sub n is going to be the original, but dividing by a fraction is the same as multiplying by the reciprocal. So on top we get n plus 1 factorial. On bottom we get 2 to the n. Awesome. And as you do more of these, you get better and better at our algebraic simplification. We'll be able to reduce some stuff here, guys. So let's rewrite that 2 to the n plus 1 as 2 times 2 to the n times n plus 1 factorial all over, and I'm going to expand this factorial on bottom partially. N plus 2 factorial is n plus 2 times n plus 1 times n minus 1 forever after. So I'll partially expand that to n plus 2 times n plus 1 factorial because we're trying to play my favorite game, the cancel game. So we'll expand that partially, knowing that we'll be able to simplify. And then I still have what on the bottom? I still have that 2 to the n. All right. Marker color change. Here goes the 2 to the n's. Hasta la vista, baby. Here go the n plus 1 factorials. And we're left with a new fraction. So here we go. The limit is n goes to infinity of what's remaining on top. On top we just have 2, is that right? And on bottom we have what? N plus 2, is that it? That's it? And so I've used my algebraic, right, manipulation and expansion to do some canceling, and all we have is 2 on top, and all we have is n plus 2 on bottom. So can we determine the, oh, absolute value too. Sorry, absolute value. I dropped the bars. Does it matter? No, we know that n is my positive integer, right, index counter that's forever positive and increasing towards infinity, so I don't need the bars. Right? I don't need the bars anymore. The ratio test has the bars though, right, as we talk about absolute convergence, which is going to be very important tomorrow or Friday. All right, so can we evaluate that expression as n goes to infinity? Absolutely. What's the value of that expression as n goes to infinity? Sophia? 0. So 0, this exists, and it's a finite number. It's 0, so what does that tell us? Well, that's less than 1. So this series must converge by the ratio test. That's pretty sweet. Raise your hand if you already got that. Marissa.
Can you use the direct comparison test? We convert it to x to the n over n factorial. Oh,
that's a great question. My hesitation with that is that you let it be x to the n. You know what I'm saying? And you're thinking x to the n over n factorial is e to the x, right? It's just that you let it be 2 to the n, which would be the same as, oh, that converges to e squared. You see that substitution? Instead of having x to the n, you have 2 to the n, yes? So that would converge to e squared, right? So then that would be okay. Then that would be direct comparison. Oh, except one problem. Oh yes, the n plus 1 is forever less than n factorial. Yes, you could. But then you should say that the other one converges to e squared. And this one is forever less than or equal to the other series. Therefore, this converges by direct comparison. That would be correct.
So you have to say it converges to e squared to be right.
No, but you should, because you now switched it into a one with the x. You know what I'm saying?
Yeah.
Vivian?
I can pull out the n plus 2 from like the n plus 2 factorial.
Great question. So right here, and that's the crux of our simplification. Pretend this was not generalized as n plus 2, but pretend it was 4 factorial, right? How would you expand 4 factorial? And on top, right, you didn't have 4 factorial, you had 3 factorial. How do you expand that? So in this expanded form, 3 factorial is 3 times 2 times 1 forever after. 4 factorial is 4 times 3 times 2 times 1, and you cancel out the 3 times 2 times 1 is really 3 factorial. We did the same thing here, but it's generalized. This is 1 higher than, just like 4 is 1 higher than 3. Instead of expanding out forever after, we just expanded out that first thing. 4 times 3 factorial is 4 factorial. And then 3 factorial left stayed the same and we cancel. Does that help some? Cool. Are we good with number 2? All right, 1 to go, guys. Let's take a look at the interval of convergence now. We have the x expression in there. So we can do this a couple different ways. Let's see. the interval of convergence. What's very powerful for this, I mean, if this had been just no n there, do you guys recognize that? If it had just been no n there, it would be direct substitution. I just take my r radius, x over 3, and set it less than 1 and solve, right? But it's got the n here. Well, does that make a difference? We'll see if it makes a difference or not. We'll go ahead and apply the ratio test. And consider, well, it's not really a test for convergence. I'm going to go ahead and just consider the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. When that ratio is less than 1, we know that my series converges. We'll determine what values of x make that happen, and then we can go ahead and find the interval of convergence. You're seeing that a lot in interval notation, like in the textbook. All right, so here we go. We need the limit as n goes to infinity of a sub n plus 1 is going to be n plus 1 times x to the n plus 1 all over 3 to the n plus 1 divided by my original. That's the same as multiplying by the reciprocal. So on top we have 3 to the n over n x to the n. Go gadron, and that equals the limit as n goes to infinity of, and let's go ahead and see if we can't do some reducing. So this x to the n plus 1, we know that's the same as x times x to the n. So I've got to leave that n plus 1. And on bottom, we have this n here. We'll put that out front. And 3 to the n plus 1 is the same as 3 times 3 to the n. You see why in advanced algebra we had to learn all those exponent properties? You know what I'm saying? Like, that's what's allowing us to do all this simplification. Kobe?
Oh, x to the n on the bottom.
X to the n is still right there. Thank you. Good. Oh, there's this little vacancy, a little spot right there just waiting for it. Awesome. Now let's switch marker color. Oh, yeah. You guessed it. There it goes. 3 to the n, 3 to the n. X to the n, x to the n. Leaving us with x, 3, and this fraction, n plus 1 over n. You do not have to regroup that out in front of the bars, but you certainly may. Remember, n is this positive integer, right? That is my counter that's always positive and it's going toward infinity. And so if you'd like to perform your analysis of the limit, you can certainly regroup this up front, but you don't have to. We want the x part to stay in the bars so that we can go ahead and set that less than 1 and solve. Right. So what happens as n goes to infinity? Well, this rational expression n plus 1 over n, you could do this multiple ways. You could use L'Hopital's rule after initial substitution would give you an indeterminate form, infinity over infinity. The derivative of the top is 1. The derivative of the bottom is 1. 1 over 1 is the constant 1, right? And so the limit of a constant is a constant. You could also multiply top and bottom by 1 over n, the largest power of n that appears, and get 1 plus 1 over n over 1. 1 over n goes to 0, so I get 1 over 1 is 1, right? We could also just do n behavior, or break this up as n over n plus 1 over n. N over n is 1. 1 over n would go to 0. 1 plus 0 is 1. So either way, you're going to get this whole thing goes to what? 1. Times this algebraic expression, x over 3. We need then this to be less than 1. So what will we do? We'll take it and we'll set it less than 1 and solve. We know that is 1/3, which you could have pulled out with the ends originally, but I don't want to mess up with our evaluation of the limit, so I left it in there. We want that to be less than 1, which means that my radius of convergence would be 3, but my interval of convergence would be, split up the bars, -3 is less than x is less than 3. So my radius of convergence is 3. My interval convergence, however, would be -3 is less than x is less than 3. Raise your hand if you got all the way. Did I make it all the way to the end? You did? Yes, that's good. That's where you need to be right now. Marissa.
So
You're not there? To the office! I'm just kidding.
you can't just like see it and be like it's similar to geometric because of that n, or like because that it works. I got the right answer, but you
Yes.
can't do that all the time.
No, you can't do that all the time. So I don't want you to get in the habit of doing that,
Yeah.
and then run into trouble when you can't do it.
Okay.
You know what I'm saying?
Yeah.
It ended up being just fine because you see that x over 3 to the n, geometric with r, you know, 1/3, but that n, it won't always be n, and it might make a difference. You know what I mean? If it's not just n.
Yes.
If it were x to the n over 3 to the n, then you could go right there right away. But that n out there, I won't want you to get in trouble. Okay?
So just do ratio test.
Yes.
Okay.
Ratio test is powerful. It's all encompassing. Does a good job. The only problem is if it equals 1, it's inconclusive, but we haven't run into it. All right, box it, and we'll go ahead and pause the recording and take care of our OTL.
Yeah.
Okay, ladies and gentlemen, let's go ahead and take a look at these two famous series. So everybody, let's focus back in. We previously investigated the question of convergence for these two famous series. That is the sum from 1 to infinity of 1 over n, a partial expansion of that, right, would be 1 over 1 would be 1, plus increment my counter by 1, right, that would give us 1 half, plus increment my counter by 1, plus 1/3, plus, and so on and so on, plus 1 over n forever after, yes? Versus the sum from 1 to infinity of 1 over n squared, right? The sum of the reciprocal squares, also a famous series. If we were to do a partial expansion for this, right, we would get 1 over 1 squared is 1, 1 over 1 is 1, plus 1 over 2 squared is 1/4, plus 1 over 3 squared is 1/9, plus 1/25, no, 1/16, plus and forever after 1 over n. So let's go ahead and think back and remember, does each converge, does each diverge, does one do one do the other? Go ahead and tell your partner. Remember these bad boys? All right. Confident? Any partner pairing confident? Yes, Tyler.
The 1 over n diverges, while the 1 over n squared converges.
Absolutely. And so the left-hand side, the harmonic series, classic, diverges, and the right side, the sum of the reciprocal squares, converges. Raise your hand if you have the same thing. So you guys remember that? Good, good. And how did we show that? So what was our strategy? We're going to put that. Diverges, converge. And what was our strategy to determine convergence or divergence? Right? You guys remember that? That's fun, Riley.
Can we compare it to like the integral from 1 to infinity of 1 over x?
Yes. Yeah, we recognize that that these terms were, let's see, they were all positive, right? They were all positive, but they were decreasing, right? And the limit of the nth term did go to 0 as I went to infinity. So we modeled the behavior of this series with a continuous function defined for all real x inputs, right? A continuous function as opposed to just a series with the domain is the counting numbers. We went ahead and expanded it to be an entire continuous function. And so if our sequence a sub n is a sequence of positive terms, and we can model that with some function that's continuous, positive, and decreasing function for all n greater than or equal to n for some positive integer. So it doesn't have to be right in the beginning, but eventually, if all of my successive terms, right, are decreasing in magnitude at some set point in the series, then the series and the integral share the same fate. They either both converge or they both diverge. In this way, right, these are not equal to one another, and yet they're connected. So we could show the convergence or the divergence of a series, right, the series a sub n, by considering the integral and seeing whether this integral, right, existed, whether the integral converged or diverged. So that was powerful. Okay. So let's go ahead and consider this new series. While this series is not the same as the harmonic series or the sum of the reciprocal squares, it is similar, right? How is this connected? Look at it, right? So how are they similar? Tyler?
It's longer than
Yeah, it's a reciprocal, right? It's a power function, some power function on bottom, and it's both one on top. So when we saw that first one diverged, we saw this one converge, and our strategy, Riley reminding us, was the integral test. So we can only use the integral test, right, if we can model those term values with a continuous positive decreasing function. Well, would that be a continuous positive decreasing function if we instead let it be a function of x, 1 over x root x? Well, yeah. What happens as x gets larger? Yeah, and we're only looking at positive inputs, and so this will always be positive. So we've got a continuous positive decreasing function. We know that if we consider this integral from 1 to infinity, then if it diverges, so too must the original. And if we consider the integral from 1 to infinity of this continuous positive decreasing function and it converges, then so too must the series. So this is a great, right, application. This is what the integral test is good for. So let's consider the integral of from 1 to infinity of f of x with respect to x, because what allows us to do that is f is continuous, positive, and decreasing. Better write that. Continuous, positive, and decreasing, so we can apply the integral test. All right, so for us that would be the limit as b goes to infinity of the integral from 1 to b of 1 over x root x with respect to x. That in turn is given by the limit as b goes to infinity of the integral from 1 to b of, can we make that cleaner, right? X times root x. We saw that kind of in our homework with ends. We can rewrite that as x to the what? 3/2 on bottom. So this is the integral of 1 over x to the 3/2 with respect to x. And by rewriting this with negative exponents, it'll be easy to apply my power rule to integrate this. Isn't this the integral of x to the negative 3/2? And we know that if my power, as long as my power isn't -1, I can use the power rule. So I'll integrate this and get x to the negative 3/2 plus 1 would be x to the -1/2. We're doing that right? Math's hard. Numbers are hard. X to the -1/2, and then divide by the new exponent. Is that right? And then evaluate it from 1 to b. So let's make this look a little bit prettier. We got x to the -1/2 on top. That's the same as 1 over x to the +1/2 on bottom. That's the same as root x on bottom. And we got -1/2 on bottom. -1/2 on bottom is the same as -2. So I'm getting a limit as b goes to infinity of -2 over root x, evaluated from 1 to b. Are you guys getting that? Did I do that all right with the signs? The negatives, the positives? All right, can we evaluate that? You bet your boots we can. This is simply the limit as b goes to infinity of, evaluated the antiderivative with the upper limit substituted in, I get -2 over root b minus a -2 over 1 is plus a +2. As b goes to infinity, right, what happens to this expression? Goes to 0, baby. Leaving you with 2, and the limit as b goes to infinity of a constant is the constant itself. And so this equals what? 2. 2 is a finite value, ensuring that the integral converges. Therefore, by the integral test, so too must the series converge. So this is a finite value. Oh, finite values. No finite value. Therefore, the series converges by the integral test. Pretty sweet. All right. The integral test is powerful, but granted, it only works for a certain class of functions. We have to be continuous, positive, and decreasing, right, in order to model behavior of a series with a function. So that could be somewhat limiting. And yet, we've got a lot of functions that look of this form. In fact, they make up their own series of own classification of series called p-series. So consider the series where the nth term is given by 1 over n to the p, where p is some, right, is some exponent. Now let's go ahead and determine whether or not this series converges or diverges. Well, there's got to be a quick way. We can do the integral test every single time, and yet, is there some break-even point, right, where we can quickly and easily discern whether or not the given series converges based on the value of the power? Yeah. What happened when n equals 1? Right, when n equaled 1, when p, the power, when the exponent equaled 1, did my series converge or diverge?
Diverge.
Yeah, diverge. What happened when my power p, which is on bottom, equaled 2? It converged. What happened when it equaled 3/2 or 1/2? It converged. And so we can show with the integral test, what do you bet that break-even point is? Yet again, 1, right? And so the integral test can be used to prove the convergence or divergence for a generalized p-series. And so a p-series, right? A p-series converges if that exponent is greater than 1. And it diverges if that exponent p is less than or equal to 1. And because we've already written it as a reciprocal, we'll consider my power being from 0 to infinity, right? Because it's already on the bottom, so we'll consider it being from 0 to infinity. So if p is in between 0 and 1, then we know that my series is going to diverge. And if it's greater than 1, right, then we know it's going to converge. Now, if we think back to our connection with limits, even back from AB, this makes sense, right? When we have n squared on bottom, that's going to just shrink to 0, and so on and so forth. All right, so now let's go back to our Bellwork. What if number 1 had been slightly different? Go ahead and compare this with your Bellwork number 1. Right, what's the difference between this one versus your Bellwork number 1? Right, what's the difference between those? Emily?
It's subtracting 4 rather than adding 4.
Yeah, that's a subtle difference and yet important. Could we have used the direct comparison test to prove convergence or divergence of this series if it had been 5 to the n minus 4 on bottom? I mean, it's a small change, particularly as n goes to infinity. Tyler? I keep coming back to you.
I know. I'm going to say no.
I'm going to agree with you. The question is, why could we not have used, right? We could have not used direct comparison any longer if it had just been a subtraction of 4. How come? What does that change?
Does it not ensure that the bottom is smaller?
Absolutely, right? This, well, it now makes the bottom smaller, which makes the value of the fraction larger than the known series, geometric 2/5 ratio, right? R equals 2/5, which we know to converge. So we do not satisfy the prerequisite of the direct comparison test where my new series, right, is not less than or equal to a known series to converge. This, in fact, is slightly greater than, right, this known series to converge. And so we can no longer use the direct comparison test because this new series, call it series A, is no longer our series B, which is our known geometric which converges with r equals 2/5 is less than 1, right? So we have to be less than or equal to a known series to converge, right? Remember when we were doing the graph with the integral test to smush it underneath and guarantee that it also converges? This is the prerequisite for divergence. And if we want to be bigger than a known series that diverges, that will ensure that it diverges. And so we think that this, we know that this converges and this is larger than it, so we can't use direct comparison, right? We cannot use direct comparison. And yet, as n goes to infinity, do you think that that subtraction by a measly 4 is going to make much difference in the overall n behavior, right, of a function, or in the sum of an infinite number of terms? No, my gut tells me no. That minus 4, right, is not going to make a difference. If n goes to infinity, right, that difference is going to be nullified. And so, so what are we going to do? Well, we need a new test. And that test, in the limit, right, we assume that this is going to behave like the 2/5 to the n. So gosh, we want to make sure that we can, we can compare it to that 2/5 to the n because we know something about it. We know that that's geometric. So in the limit, if we think that it behaves like this, then we'll use what we call the limit comparison test. All right? So it's not called the direct comparison test. It's called the limit comparison test. And it gets after that as n goes to infinity components. So the limit comparison test allows us to compare, right, with a known series that converges or diverges. It just allows us to consider in the limit as n goes to infinity. We think that's going to behave like the 2/5 to the n that we know about. So we'll perform the limit comparison test instead of the direct comparison test. We still set up a ratio, the ratio of my new series versus a known series. And again, it doesn't matter which is on top or on bottom. We're going to be able to get results here that show we'll be able to interpret our results regardless of which one you put on top or on bottom or which one you call A or B. So if we've got positive terms for some n after n forever after, then we consider the limit as n goes to infinity of the quotient of my series, the quotient of the nth term in each series. And if we get some constant like 2, right? If we get some positive constant, then that shows that the series share the same fate. They either both converge or they both diverge. Kind of like the integral test, right? They share the same fate. If the integral diverges, then the series diverges. And if the integral converges, then the series converges. If the limit gives us 0, right, and then that bottom one converges, then we know the top one converges as well. Versus if the limit gives us infinity and that bottom one diverges, then we know the top one diverges as well. Really, we're talking about them sharing the same fate here. And let's go ahead and see if we can now apply it. So this is important. You got that sheet, right? Okay, that's a big deal. So does the series converge or diverge? Well, this is what we're saying. We can't use direct comparison because that minus 4 makes my denominator smaller, right? Smaller than my known series, 2/5 to the n, which means that those terms are larger than, right? They're larger than my known series that converges, so I can't use direct comparison. If I want to use direct comparison for convergence, I need to have less than or equal to my known series comparison the whole time for direct comparison. But that's okay. We can use the limit comparison test. So we'll go ahead and consider the limit comparison test. So the limit comparison, right, lets us call this my series A, and we're going to let series B now be the one that we know something about. We think that in the long term, this behaves like, right, 2 to the n or 5 to the n, or the series 2/5 to the n, which is geometric. So we're going to let this new series B be given by again, we could write that as 2 to the n or 5 to the n or whatever. That's our known series, which is geometric with r equals 2/5 less than 1. It converges, so we know all about that. And we're going to go ahead and perform the limit comparison test. So how does that go? We consider the limit as n goes to infinity of the ratio, right, of my new series to my known series. So we'll do ratio of A to B would be 2 to the n over 5 to the n minus 4 over, bless you, Can I do multiply by the reciprocal right away for space saving? Because we did that with ratio. So we're really dividing by 2 to the n over 5 to the n. What I'm going to do is I'm going to multiply by 5 to the n over 2 to the n. Yes? And so here's our dividing by the original. And now we'll see if we can do some algebra. Well, right away, look what happens there. That's even easier than the ratio test. And let's see, we get the limit as n goes to infinity of, and now on top I get 5 to the n. On bottom we get 5 to the n minus 4. We're good at evaluating limits, right, involving infinity when we're dealing with a rational expression where I've got polynomial top and polynomial bottom. But now we have exponential top and exponential bottom. Does that hold us back? Well, no, we can apply the same technique. We could we could multiply both top and bottom by 1 over 5 to the n, just like we multiplied top and bottom by the reciprocal of the largest n power that appeared. We could multiply by the largest exponential that appeared and reduce. So watch what happens. So doesn't this equal the limit as n goes to infinity of 1 over, and then 5 to the n times 1 over 5 to the n is 1, minus 4 over 5 to the n. Did that help us at all? Well, certainly. We see now that this 4 over 5 to the n term, as n goes to infinity, this denominator goes to infinity, ensuring that this fraction approaches what? 0. Therefore, I get the limit of a constant is the constant, so I get what? 1. Is that a constant between 0 and infinity? Yes. And so this is a constant, finite value. So they share the same fate. Series A and Series B share the same fate. We've shown that Series B, my series of comparison, is geometric with ratio r equals 2/5 is less than 1 converges. Therefore, my new series A sub n must also converge, which was our gut feeling, right? It's that I bet that looks a lot like 2/5 to the n. Right. So share same fate, thus original series A converges by limit comparison test. Hey, that's cool. All right, so we slightly tweaked our Bellwork number 1 and we got a new test out of the deal. Let's go ahead and see if we can practice that a couple times. Does the series converge or diverge? Why? Okay, does the series converge or diverge? Why? Well, right away, right, we can consider the nth term test. Remember, don't lose sight of all that. If the nth term doesn't approach 0, then my series is going to diverge no matter what. As n goes to infinity, what happens to the nth term, though? As n goes to infinity, my nth term does what? Approaches 0, right? And so we can't say that this diverges right away. Now, that doesn't mean it converges. It just means it's a candidate, right? This could certainly converge. Can we use direct comparison? Well, in order to use direct comparison, we have to choose a series that we already know something about. We know converges or diverges. Well, and as I look at that, automatically the harmonic series jumps into mind, right? And I know the harmonic diverges, right? Doesn't that look like the harmonic series? I mean, it's got the multiplier, but a constant can be pulled out in front of the summation notation, just like we pull out in front of an integral. So I'm thinking that behaves like 1 over n, right? Which we know diverges in the limit. However, can I use direct comparison for this? Well, that plus 3 on bottom, right, does what to the denominator? A little bit bigger, which makes the value of the fraction a little bit smaller, which is what I want if I'm using direct comparison to show convergence, but I'm trying to use direct comparison to show divergence, so I need to be bigger than my known series. This is slightly smaller than my harmonic series, which I know to diverge. So can I use direct comparison? No. So all that to say that, no, we can't use direct comparison, we've got to use our new test, our limit comparison, because I've got a hunch that in the limit, that this must behave, right, like 1 over 4n. So I'm going to choose to compare it with series B, and I'm going to let that be my harmonic series. Because that 1/4, right, could just be pulled out front, I'm going to choose the series. Oh, I wish I hadn't done 0 there. It's okay because it's just for some n greater than 1, so I'm going to type n. Do it anyhow. So I'm going to compare with my harmonic. Okay, so I'm going to let series D be the harmonic series, right? This 1 over 4n is just 1/4 of the harmonic series. And so I'm going to choose this to be my series of comparison. So what's the limit comparison test? I consider the limit as n goes to infinity of my new one over my comparison series. For us, that would be my new one, 1 over 4n plus 3, divided by 1 over n. Well, that's the same as multiplied by n over 1. Yes? So I get the limit as n goes to infinity of n over 4n plus 3. As n goes to infinity, what happens to my rational expression? Well, initial inspection, if we're back in AB, shows that this goes to infinity over infinity, yes, which is the indeterminate form. And yet, it's an indeterminate form that authorizes the use of L'Hopital's. The derivative of the top is 1, the derivative of the bottom is 4, right? And so I get 1/4. And so, let's see. We could also do my multiply top and bottom by the reciprocal of largest power of n appears. Either way, I'm going to get that 1/4. So I get 1 over 4 plus 3 over n. What happens to 3 over n as n goes to infinity? Goes to 0. So we still get our L'Hopital's 1/4 that we predicted. You can certainly use L'Hopital's too. You could use L'Hopital's, that's totally fine. All right, so wait a minute. 1/4 is less than 1. So that means this converges? No, we're using a limit comparison test. We're seeing that if this equals some constant, then they share the same fate. Who shares the same fate? Our series of comparison and the original. And we chose purposely the harmonic series, which we know to do what? Diverges. Therefore, this must also diverge by the limit comparison test. So we're choosing our B as the harmonic series. We know this diverges. We did the limit comparison test and got a constant. Therefore, they share the same fate, so they must both diverge. So my A series diverges by limit comparison. Hey, that's pretty sweet. In fact, the math so far has been easier than the ratio test. Have you guys seen that? It's kind of been easier than the ratio test. Great. All right, so let's go ahead and try another. You guys ready to try with your partner? Want to try this one with your partner? No? Where's the gung-ho? No? Doesn't matter to me. Let's look at the original fraction. My original fraction, right, is a combination of power terms, but it's a rational expression where I've got polynomial top and polynomial bottom. Our pre-calculus gut, right, thinks that this is going to behave like the quotient of my dominant terms. And so I'm thinking in the long term, in the limit, right, this is going to behave like what? As n goes to infinity, we think this is going to behave like what? 2 to the n over n cubed would be the quotient of the original dominance, and that would reduce to 2 over n squared. So we think it's going to behave like 2 2 over n squared. So we'll go ahead and choose a comparison, right, series that is our famous sum of reciprocal squares. We don't need the 2 because it's just a constant multiplier. So I'm going to purposely choose my comparison series to be series B to be the sum of the reciprocal squares of 1 over n squared, which we know to what? Does converge or diverge? This converges by a p-series test. So this known series converges by the p-series test. All right, so let's consider the limit comparison test. If we get a constant, they share the same fate. So let's see if they share the same fate. We'll consider the limit as n goes to infinity. Don't need an equal sign. The limit as n goes to infinity of a sub n over b sub n, and that will be 2 n minus 1 all over n cubed plus 3n. And we're going to divide that by 1 over n squared. That's the same as what? Multiplying by the reciprocal n squared over 1. And now I get to do an equal sign. And so what do we get for that? Well, I'm getting 2n cubed minus n squared all over n cubed plus 3n. Yes? And if we were back to AB, we'd see that initial substitution would give us an indeterminate form infinity over infinity, right? And we can do L'Hopital's, but we have to do L'Hopital's. We can see with that exponent 1, 2, 3 times. And so I'm thinking the easier route, again, will be to use that, divide everything by the largest power of the exponent, right? The largest power term that appears, and try again. So I keep doing it instead of L'Hopital's. So what do we get? Looks like we get 2 minus 1 over n all over 1 plus 3 over n squared. Is that what you guys are getting? And what happens to my 1 over n as n goes to infinity? That shrinks to 0. What happens to 3 over n squared as n goes to infinity? That shrinks to 0. So I'm left with what? The limit of 2. And the limit of a constant is the constant, so I get 2. And guess what? 2 is a constant, so they share the same fate. Thus, that's fun to say, isn't it? Thus, original converges by limit comparison test. So the original converged by p-series test. Thus, my original converges by limit comparison. Why is that cool to me? I don't know. That's cool. That's pretty cool. All right. I love that. A series in which consecutive terms alternate between positive and negative is called an alternating series, and we've seen alternating series already, particularly with our power series representations for sine of x and cosine of x, right? That -1, we had that x, right, minus x cubed over 3 factorial plus x to the 5th over 5 factorial. We also saw it with our cosine, right, our 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus ... So an alternating series, right, we've got terms which alternate in sign. Well, that makes sense. We've already seen, and then we use alternating series air-bound to estimate the error of our Taylor polynomial wherever we truncate it. And so if we only went to the 4th order Taylor polynomial, we could get an error-bound for an alternating series by considering the magnitude of the next term, right? That first truncated term. Well, let's go ahead now and take a further look at alternating series in general. Sometimes these series converge, sometimes they diverge. And so they're their own category of functions, and yet we need to be equipped to handle them because we'll have to be able to do our regular convergence versus divergence tests and justification when they're thrown in the mix. And so we haven't done much with these. Let's take a closer look. Consider the following three examples. 1 minus 1/2 plus 1/3 minus 1/4 ... What does this resemble? What does that look like? What does that look similar to? Riley? Yeah, our harmonic series, right? The difference here is that we've got alternating signs. And so instead of being 1 plus 1/2 plus 1/3 plus 1/4 plus ... 1 over n ... we get that alternating signs. And I'm wondering now, does that make a difference, right? Does that make a difference? Well, turns out that it makes all the difference, right? If we consider this, we've got 1 minus 1/2. We could go ahead and consider, right, whether or not this converges or diverges, and we could do that by, well, let's try the ratio test, because that's our absolute value, right? So we can do the ratio test and see what happens. And if we were to do the ratio test for this, right, what would we get? Well, we get -1 to the n plus 2. You guys see that? Over n plus 1. Divided by a sub n would give us the original multiplied by the reciprocal, so I get n over -1 to the, what's that? Plus 1. And you guys have been practicing simplification with ratio test last time, so does this reduce nicely? Let's see. So -1 to the n plus 1 and -1, so I'm just getting -1 left over on top. Is that what you guys are getting? Times n over n plus 1. Okay, can we do anything here? Well, what's -1? What's the absolute value of -1? 1. So we don't need this inside. We get the limit as n goes to infinity over, I'm sorry, of n over n plus 1. All right. So we've generated an expression, right, where we just have n's in it now, and we're trying to evaluate the limit as n goes to infinity. Our method for arriving here was what? What test did we use? The ratio test. As n goes to infinity, what happens to this expression? Tyler? The top goes to infinity. Yes. What does the bottom do? Yes. What's the value of the fraction do? Goes to 1, doesn't this? Right? We could do L'Hopital's rule and get 1 over 1, and the limit of a constant, the limit of 1 is 1. And so, for the first time, we've reached, right, a value of exactly 1 with our ratio test. What does the ratio test tell us when the value of our quotient is 1? Inconclusive. And so the first time we've got to an inconclusive situation, okay? We know one thing for sure, and this will be very important on Friday, is that this does not converge absolutely. This does not give absolute convergence. If it converged absolutely, we would have gotten a constant less than 1. And that's what the absolute value bars have to do with here. So if we consider the ratio test with absolute value bars, we get something that converges absolutely on that interval, which means that it converges with the strongest type of convergence. Here we have equals 1, which means that we don't know whether this converges or diverges. So what we'll do is we'll go about it in a different analysis, and this is perhaps one of that's probably the second most famous series, is the alternating harmonic series. Okay, so let's go ahead and consider a number line. Let's go ahead and consider a number line, and let's make this and 1 and 1.5. Okay. Let's consider the series of partial sums. What? Well, remember, for a series to converge, then the limit of the partial sums as n goes to infinity must converge. That must equal a finite value. If the limit of the partial sums converges, then the series converges. If I consider the first several partial sums, that is s sub 1, it's the value of the sum of the first term, which is 1. If I consider the next partial sum, s sub 2, that's the value of the first two terms summed together, and I get 1 minus 1/2 is 1/2. If I consider s sub 3, the third partial sum, I get 1 minus 1/2 is 1/2, plus 1/3, oh gosh, 3/6 plus 2/6 is 5/6. Are you guys seeing that? All right, so let's go ahead and play along with it. We're going to now plot the partial sums. Ready? S sub 1 is 1. Oh, I wish I did that in green. How bad did I do? I wish I did it in green. Bad enough? Second partial sum, s sub 2, 1 minus 1/2 is 1/2, so where am I there? Here's my s sub 2. S sub 3 is 5/6. Where's 5/6? Well, 5/6, if this is 1/2, this is 1, this is 1/2, so 5/6 is what? Right about here? Yeah? In red? Quick check. Okay. S sub 4, and we get our calculator anytime. S sub 4 then does minus 1/4. So go ahead and do 5/6 minus 1/4, please. Somebody más rápidamente. Go if I win. 7/12, which is just decimal me, baby. So 5/6. So 0.5 is then right here, yes? That's S sub 4. Okay, 0.58, and then plus 1/5. 0.78. 0.78, and so where's that? Well, 0.8, that was 0.83. 0.78 then is right here. Is S sub 5. And as we continue doing this, we add and then subtract alternatingly a smaller and smaller magnitude. If you consider visually the plot of the partial sum that then goes to infinity, would you say that this series converges or diverges, and why? This series must converge because the limit of the partial sums converge. In fact, it's approaching a particular value, oscillating back and forth and back and forth and back and forth to some number, call it L, in the limit. And so it ends up being ln2. Crazy? Yeah, that's pretty crazy. It ends up being ln2, the natural log of 2. But forever oscillates back and forth, approaching a value. That sounds a lot like 1. So is there a particular value, right, that the expression approaches, in this case the partial sum s sub n, as n goes to infinity? Yes. If so, then the limit exists. And if the limit exists of the partial sums, then the series must converge as well. So this series converges, and it's the second most famous series ever. It's the alternating harmonic series. If we wanted to provide a rationale for that, it's a lot shorter than our lengthy discussion graph, because the limit of the partial sums exists, is finite and exists, therefore the series converges. That's pretty awesome. Okay. Looking more and more like 4/6, isn't it? All right, let's take a look at number 2. -3 plus 1 minus 1/3 plus 1/9 minus 1/27. Is this an alternating series? Yeah. It looks like my terms alternate forever and ever after a particular one between positive and negative, and that's a dead giveaway for the generalized nth term, the -1 to the n, or n plus 1. And then n over n, 9/3 to the n. I hope it doesn't take as long as the last time. Does anybody recognize this? Well, let's do a quick rewrite. Couldn't we rewrite that as says 9 times and 9 these both to the same exponent? So we could write that as -1/3 to the And if I rewrite it like that, why is that useful? Well, because now we recognize this is geometric with ratio what? Yeah, -1/3. And the magnitude of -1/3 is less than 1, so converges. So we didn't have to do a long lengthy test. This converges geometric with r less than 1. Magnitude of r less than 1. That's easy. And 1 to go. 1, -2, +3, -4, +5, -6. Nice pattern here, right? Is this alternating? Absolutely. Telltale with my generalized nth term. Does it converge? Well, it looks like we're always going back and forth and back and forth, my partial sums, and yet, is there a particular value that's being approached? No, it's always a little bit higher than, a little bit lower than, a little bit higher than. So because this oscillates forever and ever, right, this is not converging towards a particular value. The limit of the partial sums does not exist, and so this diverges, and we could do a test by the nth term test. Look at that. As n goes to infinity, I get, right, my magnitude of my nth term goes to infinity or negative infinity, alternating, right? And so this diverges by the nth term test. The limit as n goes to infinity of the nth term does not equal 0. So the series diverges by the nth term test. All right. In today's whirlwind discussion, it was my hope that you helped to solidify, right, the difference between direct comparison versus limit comparison, right? When we can't quite use direct comparison and yet we've got a hunch of a known series that we know converges or diverges, we can use the limit comparison, and the algebra is easier than the ratio test. Meanwhile, ratio test still solidifies its spot as a powerful tool that encompasses a broad category of functions. When in doubt, you can try the ratio test and see what happens, right? So that's an inclusive, powerful tool that allows us to determine not just if a series converges or diverges, but also the interval of convergence for a power series. So that's a big deal too. All right, so let's finish up our alternating series, and then we can do our closure. So our alternating series test, then, we can apply to those three in much shorter, right, much shorter than our lengthy analysis of each, if we have an alternating series, right, where this just means that they alternate in sign. So the way that this is written here, so terms alternating in sign. So if my terms alternate in sign, because we wrote it as plus, minus, plus, minus, plus, minus, so each of those U's is positive, is just a long way of saying that my terms alternate in sign, right, in order to apply the alternating series test. And the terms decrease in magnitude after some positive integer n. That means they're all getting smaller, right, at some cutoff point. They're forever after decreasing. And that all important if the limit of the nth term is 0. Then we can say the original series converges by the alternating series test. Do these prerequisites look familiar? We've seen those prerequisites before, right? They look familiar from my alternating series airbound, when we were saying what's the magnitude of the next term. Well, if my terms alternate in sign, they decrease in magnitude, and the limit of the nth term is 0, right? Then we know that the truncation error based on the nth order Taylor polynomial was less than or equal to the value of the next ordered term, right? The very next term, the a 7 plus 1th term. Well, if our series satisfies the same preconditions, then we can say it converges. The deal is that it doesn't converge absolutely unless the ratio test with absolute value bars equals a number less than 1. And so the difference between converging absolutely and converging conditionally is going to end up being a big deal when we test our endpoints on Friday. A series that converges Absolutely. With the ratio test and absolute value bars, producing a value less than 1, that's the strongest type of convergence, right? And that means that it will converge no matter what we do with the terms, whether we rearrange them, right, however we want, it's always going to converge. Versus a series that converges conditionally, where the absolute value bars, the ratio test does not result in a value of 1, but just converges conditionally by the alternating series test, then that's not going to be a very strong type of convergence. It still converges, right? It's just that if we were to manipulate the order in which we apply those terms in the sum, we could create a series that diverges or equals any predetermined value. And we're going to look at that more on Friday. So that's pretty interesting. The moral of the story in the preview is that absolute convergence is the top, right? That's the best type of convergence. That guarantees convergence no matter what. All right, let's close up for the data. The P series given by the series 1 over n to the p converges if blank, diverges if blank. Don't say it out loud. Written response in every way, please, and be ready to share. In the limit comparison test, what happens if the limit of the ratio of series equals a constant? And B sub n, my series of comparison diverges. What can be said about my new series A? Same test, but now if B converges, what can be said about my new series A? And then the preconditions for the alternating series test. Please be ready to share. You guys all ready to share? Oh, you guys are fast. All right, so what's my break-even point? The P series converges if what's true? Danny?
P is greater than 1.
Good, and that is strictly. The P series diverges if what's true? Kobe?
P is less than or equal to 1.
Good, thank you. In the limit comparison test, if the ratio of series A to B equals a constant and B diverges, what can be said about my original A? Vivian? Yeah, also diverges. Thank you. If the limit comparison results in a constant, and I know that B, my series of comparison, converges, what can be said about my original A? Emily?
It converges as well.
Awesome. Converges as well by the limit comparison test. And lastly, 3 prerequisites. And so in order to apply the alternating series test, which guarantees convergence for alternating series, that alternating series must have what 3 prerequisites satisfied? Courtney? Good. Terms alternate in sign. That seems kind of like a important requirement to apply the alternating series test. We have to have our terms alternating side. Either that or too much to include. That's a given, okay? So we've got to have terms alternating sign and, right, what else? Sydney?
The terms decrease in magnitude at some point.
Good. So the terms have to decrease in magnitude after some positive integer n, forever after. We need each next term to be less than the previous term. And the final prereq, Grace?
The limit of the nth term is 0.
Good. The limit of the, oh, already limit. The nth term must go to 0, then goes to infinity, right? If these 3 are satisfied, then the series converges by alternating series test. That's also known as Leibniz theorem. And those are similar to their prerequisites for the error bound before. Great work today, you guys. So I have a plus question mark here. I think what I'm going to do is just go ahead and focus on these. We'll take a look, right, in more detail at the interval of convergence and endpoints on Friday's discussion. Again, we could still have the test Tuesday, the 4th. That would be a shorter lesson on Friday with built-in review time. We could also have the test on the 6th. I haven't quite decided yet, but we did have a good discussion today and accomplished our objective, and so we are on track for either, bless you, for either of those. I'll go ahead and save the recording and leave that up for a little bit for you guys to get the OTL down.